Hi Kidlets, this is your last lecture presentation before your test, which is going to be on Friday. There are going to be a couple of slides I'm going to skim through pretty quickly, so if there's information on there that you need to know, you can just pause it so that you can get that. So I created an outline here for you, so if you're taking notes, which you could be, these would be good things to put into your notes. And there should have been a 1 right there. So if you set up your notes like this, you could just fill in each of these areas. So we've already looked at the families of stars and the properties of stars. The last thing we're going to look at is how we organize all that information. So we've looked at temperatures, we've looked at luminosities, and instead of setting up a graph, we use something called the HR diagram, Hertzsprung-Russell diagram, as a way to quantify and visualize each of these properties. So we can do this for individual stars, we can do it for star clusters. So here is the basic HR diagram. So you can see already right off the bat, some of the colors should stand out to you. So you know that temperature is going to be one of the functions we're looking at. So you can see that we've got the red over here, we've got the blue here, and you also see this line along the center, which is called the main sequence. And there's our sun. So the main sequence is where most stars end up falling. And you also see that we've got a size component as well. So we've got the larger stars at the top, we've got the smaller stars at the bottom, cool stars at the right, hot stars at the left. So here is that again, which with each of the categories pretty clearly labeled. We've got white dwarfs down here, so you can see small stars, but these are also hot stars. Our larger stars are towards this top. Here is our cool big stars, here's our hot big stars, and here again is our main sequence along the center. So we can think about the HR diagram as organizing different information, similar to how we would organize people. If we had a graph that was looking at people, we could organize that the same way. So generally, the taller you are, the more you weigh, and the shorter you are, the less you weigh. So if you think about someone that is, 7'2", like Yao Ming would be way up here. Miss Hirst is going to be way down here. But there's also going to be exceptions and anomalies. So such as the supermodel is going to be way over here. A dwarf is going to be way over here. So here's a blank HR diagram. For simplistic purposes, we are only going to deal with temperature, and we're just going to call this whole side luminosity. It is logarithmic, but we are not going to deal with it in that sense. So we're just going to call this luminosity. So you just need to know the brighter stars the more luminous stars are going to be measured on this side. We are not going to deal with the magnitude portion of this. And the spectral classification, I wouldn't make you label, but just so you would know, your O stars are going to be on this side, and your M stars, your cool stars, are over here. So then our main sequence would be along the middle, from the top left to the bottom right, and we would have our giant stars here, but these would be red. Never mind, I can't change the color. And these would be our supergiants, these would be our white dwarfs. So here again is the relative sizes. And here are some of our common stars. So we've got Betelgeuse, we got Rigel, we got Polaris, here's our sun. But notice we've also got these dashed lines. These dashed lines are radius. So somewhere right in here, anywhere along this line is going to be 100 times the sun. Here's as large as the sun, here's 10,000 times the sun. So mass is the main determining factor of where a star falls along this main sequence. So the main sequence is where stars are happily burning hydrogen fusion, fusing together to form helium, and they spend about 90% of their life doing that. But if a star is born somewhere up here on the main sequence, they burn through all of that hydrogen significantly faster. So stars that are up here only live to be about 30 million years, whereas stars that are down here live to be about 3 trillion years. So mass not only determines where it falls along here, but it also determines how long it lives. So the consequence of that is that we have a universe filled with smaller, cool stars, because these very large stars, your type O stars, live such short lives that we don't see them as often. So we have a universe full of stars like this, like our sun. And we have many stars that are very low along the main sequence that haven't even evolved off of the main sequence yet. So here is a little pie chart showing that same thing. So you can see a fraction of the stars in our universe are these type O large blue stars, whereas most of them are sun-like. And we can see that when we look at plots of the stars closest to us as well. So here are the 80 stars closest to us, and you can see there are no giant stars whatsoever. So one of the reasons is because these were all born in the same nebula that formed our sun. So these are all lower main sequence stars, low mass, low luminosity, as opposed to our bright stars. So these are the 100 brightest stars in our sky. You can see there's no low mass stars. So I asked you here, why are they so bright? So in the previous HR diagram, they would be bright. Would it be because of their distance or their luminosity? And it should look very different than this one. So here, these are much larger, more luminous stars, which would be what determines their brightness, as opposed to our closest. So the main sequence is a really important function of a star's life because this is where they're in equilibrium. So stars that are in equilibrium are not getting bigger, they are not getting smaller, they are stable. They're happily burning hydrogen at a constant rate, producing helium. So when they're in this state, they're balanced. And they spend about 90% of their life there, which means we find 90% of stars there. This is what our sun is currently in. It is on the main sequence. So here's a little picture of hydrostatic equilibrium. So we have fusion that is providing that force out, but then we have gravity that's providing that force in. And it's in balance the whole time it's along the main sequence. So like I've already said, mass is the main factor that determines where a star falls along the main sequence. And we know how big a star can be when it is in a binary pair because we can use Kepler's laws to determine their rate of motion around each other. If it's not in a binary and it's not close, this is really tough to determine. But most stars are in binary. So here's a picture of that again. Over 50% of the stars we see are not single stars. So if we can determine where this balance point is, we can determine their rotation rates and we can determine their mass. So real quick, some ways to detect binaries. Sometimes we can measure them visually. Sometimes it's because of their Doppler shift, and sometimes it's because of intensity variations or spectral lines. Here's a little picture of each of those. Very few binaries can be detected visually. They would have to be very, very close. Some, when we look at their spectral lines, so at different time frames, we can detect differences in the spectra, so it means there has to be a second one there. We've already looked at Doppler shifts, the red shift and the blue shift. We could detect it that way. And then when we were at JPL, they talked about using the infrared to detect intensity variations. So when it would go in front, it would dim the star, and when it would go behind, you would have a greater intensity. And at JPL, they talked about the opposite, measuring the decrease when it goes behind. That's it, guys. Also, make sure that you watch the last video for when I mentioned the change in your solar observation. Those of you that have seen it, please keep that to yourselves so that everyone else will actually have to watch that. Remember, you will have the notes quiz here for this material on Wednesday.